Good morning, everyone. Thank you so much for joining us for another webinar of induced seismicity. On behalf of the webinar committee, welcome to this monthly webinar. Today we have Wenhan Soon from the University of Alberta. The topic of his talk is Rupture Cascade initiated by wastewater disposal, nucleation, and domino effect of the 2020-2023 earthquake sequences near Peace River, Alberta. In the following months, we have scheduled webinars by Men Andrin, Mir, and Valentin Gischik from ETH Zurich on December 5th, 2025. And after that, on January 9, 2026, we have a scheduled webinar of Kyung-Jae Im from Caltech. Before proceeding further, I would like to have an announcement of the webinar, the ARMA Symposium, 60th ARMA Symposium, which will be held in Tucson, Arizona, which will be held on June 20 to 24. The link is right here. The subject areas are petroleum, conventional and unconventional, civil, geothermal, mining, interdisciplinary, storage, and sequestration. And also the topics of interest are fundamental and experimental rock mechanics, innovative laboratory and field testing, imaging and non-destructive testing, induced seismicity, hydraulic fracturing, wellbore and drilling mechanics, enhanced geothermal systems, subsurface hydrogen storage and underground mining, slope stability, and more. The abstract submission deadline is November 19, 2025, and the link is at the bottom of this slide. I'm chairing a session on subsurface hydrogen storage, so we appreciate your abstract submissions in this conference. And I strongly encourage that you attend this event and share your thoughts and your latest findings and discoveries in this conference. So before starting the webinar, please feel free to share the webinar invites with the interested colleagues. Please contact us if you are interested in receiving notifications for upcoming webinars, and let them know that we have a distribution list. We can add your colleagues who are interested in this topic to be added to that list. Please submit your questions during or after the talk in the chat button at the bottom of the Zoom meeting window. Please send these questions to everyone. This meeting is being recorded and will be shared in our YouTube channel. The link to this YouTube channel can be found in the invitation email. And also, I would like to read some lines of Wenhan's bio. He is a PhD student of geophysics at the University of Alberta. He specializes in seismology under the supervision of Dr. Jeff Gu. His research focuses on injection-induced seismicity, seismic array techniques, and the structures and dynamics of the mantle transition zone. He is a recipient of the 2023-2024 Alberta Innovates Graduate Student Scholarship. Without further delay, let's invite Wenhan to take over the stage and present. Wenhan, thank you for presenting for us.
Thank you so much for the introduction, Maddie, and also for the invite to give this talk. I'm going to share the slides. Oh, it says only one presenter can share at a time. Do you need to
stop
exit?
sharing?
Oh,
Yes.
okay, sure. Sounds good. Is my screen looking all right?
Yes.
Sounds good. Okay. Okay. Check. Okay, hello everyone. It's a great pleasure to present here at the ARMA TCIS webinar. So first, I would like to thank Ryan Schultz from ETH Zurich for recommending me for this talk. So this study focuses on the 2022-23 earthquake sequences near Peace River, Alberta, which are likely caused by long-term disposal activities associated with oil sands recovery. So over the past 3 years, our co-authors have put in great efforts on this work. And in this talk, I'm going to walk through the key findings regarding the nucleation and evolution of these sequences. So the earthquake sequences is located at near the town of Peace River in northwestern Alberta. And there has been some sporadic seismicity occurring in that region since 2014. And on November 23rd, 2022, the seismicity rate sharply increased. And after 1 week, this region was shook by a ML 5.6 event on November 30, 2022. And in this talk, we're gonna call this event as the main shock. And after this main shock, the seismicity rate uh, drops rapidly. But after 4 months later, there's another resurgence with two large events on March 16, 2023, that occurred within 13 minutes. So first, I'm gonna provide some background information on the regional hydrology and disposal activities related to this study. So the sequences are located near the Peace River Arch, which is northeast trending cratonic landmass. So this Peace River Arch has experienced multiple stages of tectonic events. Before Middle Devonian, this arch was mainly exposed to the surface due to the tectonic uplift. And after that, in late Devonian, the arch started to subside downward below the sea level. And that's when some coral reefs start to grow along the arch edges. And these reefs buildups are now known as the Upper Devonian Leduc Formation. And this Leduc Formation is the major basal sedimentary unit in this region. So on top of the Leduc Formation, this reef formation is capped by the Ireton Shale, which is the most important water inhibiting unit in this region. So this so-called aggregate significantly isolates the water flow below and above the formation, below above layer. And right below the Ireton Shales, this Leduc reef is also partly encased by the Duvernay Shale. So these two sequences of shale layers together with the Leduc reef form a very unique geological framework in this region, which is called the PRA fringing reef. And this PRA fringing reef is highlighted on this map by this yellow contour. And this reef belt is wider in the middle and becomes narrower to the south and northwest. So this Leduc Reef Formation has been the key target for regional disposal activities. And near the epicenter, the main shock region, there are a total of 7 disposal wells near this region, targeting the Leduc Reef Formation. And near the main shock region, the Leduc Reef is around 1.8 kilometer deep and around 200 meters thick. And the earliest disposal well, which is located around 33 kilometers northwest of the main shock, started injection in 1986 and has injected over 50 million cubic meters of wastewater into the Leduc Reef Formation. In contrast, the well 1418, which is near the main shock, started injection in 2012 and has injected over 1 million of cubic meter of fluids into this reef formation. So above the Ireton Shale, the cap rock of the Leduc Formation, there are also a couple of sandstone layers and carbonate layers, which are also good reservoirs for disposal. So these permeable aquifers are, together with the Leduc Formation, are shaded in yellow on this red panel. And these layers are also interbedded by some low permeability aquifers, such as the Banff Formation and the ARMA member from the Peace River Formation. So these shale layers act as the same function as the Ireton Formation, and they are shaded by the green color. And near the main shock zone, there are a total of 3 disposal wells. And in addition to this well 1418 that targets the Leduc Reef Formation, There's 614 targets on the Permian Belloy Formation at around 800 meters. And there's another horizontal well 1425, which targets the pad member from the Peace River Formation at around 400 meters. So this deep injection well 1418 was linked to the seismicity, especially to the main shock by Schultz et al. According to the spatial temporal associations between injection and seismicity. And the induced nature of this seismicity was later reinforced by following studies like Baptiste et al. And Selbit et al. In 2024. So all these studies suggest hydraulic connectivity between the basal reef formation and the pre-existing Precambrian basement fault structures. So the fluid injected into the Leduc Formation migrated along the basal sediments and then penetrated downward into the fault plane, and which increased the pore pressure within the fault zone and nucleated the seismicity. In contrast, the shallower bitumen production, typically in the blue sky formation, likely only has a secondary contribution to the seismicity. So a key issue for this study is that they only rely on a handful of stations near the epicenters. And this led to some substantial uncertainties in even locations and has caused some debate on the fault geometry. For instance, Schultz et al. Suggest the injection actually reactivated a single fault with a reverse slip. And in contrast, Baptiste et al. Suggest 4 subparallel faults that are truncated by another conduit fault. And also there are some additional questions that are unsolved in those studies, such as which well or wells actually triggered the seismicity. Is it only is the well nearest to the main shock, the 1418 targeting the Leduc Formation only responsible, or are there other wells that jointly trigger the seismicity? And another question is, what caused the resurgence of seismicity after 4 months? Is it still because of the ongoing injection, or there are other triggers? So to bolster the seismic station coverage near the epicenters, the Global Seismology Research Group from the UFA, University of Alberta, collaborated with the Alberta Geological Survey to install a small array of geophones near the epicenters. And we call this array the PRISM, short for Peace River Induced Seismic Monitoring. And this small array consists of 10 nodal geophones. And this project started on December 6, 2022, only 1 week after the main shock. And it was extended until April 14, 2023, after 2 respective servicing field trips. So we placed 4 stations near the epicenters. So station 8 to 10 are close to the main shock zone. So the circles indicate the event locations taken by the EGS. And we place another 6 units away from the center of the seismicity to ensure the spatial coverage for this local seismic monitoring. So this study is actually based on this local array data, so which is the foundation for this study. It enables more detailed and refined seismological observations than before. And in this talk, we're going to walk through and mini solve these 3 questions. So first one is, what does the fault geometry look like? And the second one is, which disposal well or wells are responsible? And the third one is, what causes the seismicity resurgence after 4 months? So the first question can be largely solved by our seismological observations, thanks to our local array data, and including the event catalogs and focal mechanism solutions. So first, we adopted event detection location workflow and adopted this workflow to the PRISM array and the regional ribbon network. And from these 2 datasets, we individually obtained 2 separate catalogs. So from the PRISM array, we obtained over 2,000 events from December 6, 2022 to April 13, 2023. And this the magnitude of the events can reach as low as minus 1.4. And from the ribbon stations, we identify 287 events from November 23rd to 2022 to April 4th, 2023. And there are 144 events recorded before the operation of the prism ray. So our our event catalogs capture the key and very unique spatial patterns of the event swarms. And this figure shows the insert ground displacement after November 30. That's the occurrence time of the main shock. And the red color indicates the upward ground displacement, and the blue color indicates the downward displacement. And these three squares, green squares, indicate the location of the nearby disposal wells. And from the ribbon network, we identify a total of 7 foreshock together with this main shock, which is highlighted by this purple star, the foreshock main shock sequence. So this foreshock main shock sequence is located in the center, at the center of these 3 disposal wells. And the sequence is also closely located close to the center of the ground displacement. So after the foreshock main shock sequence, the seismicity rapidly migrate toward the northwest and the southeast and form 2 seismic clusters, which are robustly captured by the prism ray. So these 2 clusters are the cluster A, which is northeast southwest striking cluster, shaded in blue color, and the northwest southeast striking cluster B, shaded in yellow. And these 2 large events on March 16, 2023 come from the cluster B, and they are highlighted by the purple stars together with the main shock. So these 3 largest events form a linear pattern along the northwest southeast orientation, and the strike angle is consistent with the strike of cluster B. And furthermore, the cross-sectional, the depth view of event cluster A is shown on the right side along the strike of this cluster. So in this panel, the x-axis is the distance in kilometers, and the y-axis is depth in kilometer. And within the panel, the basement and the sediment are highlighted by different color, and their boundary at around 2.2 kilometers. So from the depth view, suggests the cluster A is a northeast deeping, highly linear cluster, which is mainly located within the basement. And this deep angle of this cluster transitions slightly from 60° in the shallow parts to around 40° at the deeper parts. In contrast, cluster B is also a northeast deeping cluster, and the deep angle is around 55°. Different from cluster A, this cluster is located both in the basement and along the basal sediment. And the basal sediment swarms are closely located near the injection well 1418. And our second observation is focal mechanism solutions. So from the events detected by our local ray, we resolved around 400 focal source solutions, focal mechanism solutions. So on the left panel, we list some sample solutions from both the event cluster A and cluster B, and they are shaded by blue and yellow color. So in summary, cluster A is represented by northeast-southwest striking, northwest deeping, oblique strike steep fault. And cluster B is dominated by a northwest-southeast striking, northeast deeping reverse fault plane. And we also highlight the visuals, the focal mechanisms for these 3 largest events on the left panel using this purple color. And all these 3 large events show a reverse fault slip, and their strike and deep default geometry are consistent with the solutions observed in cluster B. So now, by combining all these observations, we're able to answer the first question, the fault geometry. So first, all the event distributions, the locations, including the cluster A, cluster B, and the foreshock main shock sequence, can be well fitted by a northwest, southeast trending, northeast deeping fault plane. And the map view of this fault plane is shown on the right panel. And here we call this fault plane the main shock fault plane because it includes the main shock zone. And on this map is color coded by the depth, and this blue color indicates deeper, and light color indicates shallower. And here we also this dashed red lines indicates the boundary of this estimated fault plane, which is a conservative estimate for this entire fault plane that covers the main shock and these two large events on March 16. And this fault plane has a dimension of 6 kilometer along the strike and 5 kilometer along down deep. And now we're able to compare the geometry of this main shock fault plane, which are robustly captured by different observations. So here from the bottom to top, we shows the fault geometry estimated from the source solutions, the geodetic data modeling, and the 3D event fitting, which is shown on the left panel. See, all these results show a very consistent outcomes, which suggest a strike angle at around 300 degree and a northeast dipping angle. So this suggests this region are actually dominated by a single reverse fault slip, which also echoes the conclusions from Schultz et al. In 2023. However, for cluster A, so this cluster is highly linear. It has a very different strike direction compared to the other seismicity. And also we observe some strike slip components in this cluster. So that actually suggests some additional structural controls over this fault system. So here we did similar plane fitting only to this cluster A. So the best fit plane geometry is just a northeast, southwest training, and southeast dipping fault plane. And this strike angle is around 220 degree. And this angle is around 40 degrees smaller than the strike angle estimated from the cluster A source mechanisms. And also the dip direction of these two estimates are actually nearly the opposite. So despite these differences in these two estimates, both the estimates suggest a northeast-southwest trending structures with a high dip angle, almost vertical plane, located in the northwest of this main shock fault plane. So now we're able to answer the first question. So first, this region is dominated by the main shock fault plane, which is a northwest-southeast striking fault plane dipping toward northeast. So this fault plane hosts the majority of the events detected in this study. And then to the northwest of the main shock fault plane, it is truncated by a conjugate fault plane, which was also suggested by Vesura et al. 2023. So here, given the local maximum horizontal compressive stress orientation towards northeast, this geometry of the main shock fault plane is well aligned with observed reverse slips on those seismicity. And this also explains why we observe some strike slip motions along in this cluster A. And I forgot to mention these two conjugate structure actually form a linear intersection, which is a linear fault zone. And this linear fault zone is likely the location that hosts the seismicity cluster A. So the second question is about which disposal wells are responsible for the seismicity. So to answer this question, we use the fluid flow simulation software to simulate the pore pressure changes produced by injection at different wells. So from the simulations, we can identify which well actually transmit the fluid pressure from the injection targets downward into the basement fault. So first, let's revisit the event locations relative to the disposal wells. So from the map view, cluster A appears to be located near these two shallower injector 0614 and well 1425. However, from the depth view, the majority of the events are well below these two shallow injectors. And the minimum distance between the well 0614 and the cascade A is around 1.5 kilometer. In contrast, both the map view and the depth view suggest the seismicity is directly connected to this deep injector 1418. And what's even more interesting is this cluster B delineates a pathway of seismic migration starting from the injector and migrate along the Leduc formation, which is highlighted by the blue color, and migrate downward and further move downward into the basement faults. So this actually reinforces the major conclusions from previous studies about the hydraulic connectivity between the Leduc reef and the basement faults. So to further support these observations, we conducted numerical simulation to simulate the pore pressure changes produced by different different injectors. So here we designed a 3D numerical model, which is composed of sediments with a thickness of 2 kilometers, and then a basement underlying the sediment with a depth ranging from 2 to 9 kilometers. The detailed sedimentary units is shown on the left panel, which includes multiple layers of aquifers and aquitars that are shaded in yellow and blue colors. And in the basement, we include a basement fault zone, which is a northwest-southeast striking, northeast tilting fault structure. This structure is designed according to our main shock basement fault inferred from the seismic observations. And also, we designed the boundary for the Leduc formation, and this boundary is highlighted on the right panel, shown by this rectangle. And in the end, we placed 3 injectors on top of the model, and the location, injection depth, the monthly injection volume, and the injection period are are designed based on the actual records of these 3 individual wells. So the key parameter for this modeling is called hydraulic diffusivity, which describes how fast the fluids can flow in the formation. So typically the aquifers and fault zones have higher diffusivity value compared to the aquitars, which means that they have much higher capability of transmitting this fluid flow. According to previous studies and these regional measurements of the properties for each sedimentary unit, we vary the aquifer diffusivity from 0.1 to 10 meter square per second in this study. And for the fault zone, we vary the diffusivity from 0.01 to 1 meter square per second. And we assigned very low diffusivity value for the aquitars, which is around 10 to the minus 5 meters square per second. So here we show a depth view of the D value along the cross-section, cross-cutting the basement structure, the fault structure. So on this right panel, the horizontal axis is the distance, and the vertical axis is the depth. And this image, the color indicates the different values of D on the logarithmic scale. And the aquifer and the fault zone are mainly shown by the white color in case they have higher value of diffusivity. And the aquitars, together with the background basement, have lower diffusivity, and they're shown by the blue color. And within the sediment, the location, the injection depth of these 3 wells are also overlaid. And this horizontal thick line is the Ireton Shoal, and below that is the Leduc formation. So we have used this model to conduct systematic simulation under different parameter setting. But our first take-home message is that no matter how we change the aquifer and fault zone diffusivity, as long as we place the aquitars with low diffusivity on top of the Leduc formation, we found that only the injection at the well 1418 can transmit the pressure into the basement. And these other 2 injectors are actually well isolated. The pore pressure generated by these 2 wells, the shallow wells, are isolated by the Ireton Shoal and the above aquitars. So here, I'm going to only show these results under the specific parameter setting, the aquifer diffusivity and fault zone diffusivity, which is the optimal parameter according to our sensitivity test. So this is the cross section, the depth view of the pore pressure distribution along the strike along cross section that cross-cut the basement fault structure. So in this map, the horizontal axis is the distance along the cross line, and the y-axis is the depth in kilometer. And the image, the color indicates the level of pore pressure changes, with dark color indicating the higher pore pressure level, and the light color indicates the smaller pore pressure level. So this cross section actually clearly shows which well that the deep well 1418 injected fluid into the Leduc formation and propagate pore pressure into the basement. And this is the location of the basement fault. So in contrast, the pore pressure generated by these two shallow injectors are isolated. And you can see this light color strip below these two dark colors, which indicates that the pore pressure are isolated. So we then take a step further to investigate the pore pressure evolution within the basement fault. And this plot shows the x-axis is the year, and 2012 is the start of the injection at the well 1418. And the y-axis is the pore pressure increase in megapascal. And on this figure, we also put in the temporal distribution of events detected by ADS in the same coordinate. And the second y-axis is the magnitude, event magnitude. So starting from 2012, that start of the injection, the pore pressure started to accumulate, to increase within the basement fault. And in 2021, this pore pressure level reached around 0.01 megapascal, which is a commonly used threshold for the seismicity triggering. And this timing is actually correlated with this small seismicity cluster that also occurred in 2021. So after that, the pore pressure continued to increase and reaches around 0.012 megapascal right before the nucleation of the main shock. So it's worth noting that this level of pore pressure is just above the threshold of 0.01 megapascal, which indicates that the basement fault was already critically stressed before the start of the wastewater disposal. Okay, so we further compare the contribution of this nearby well 1418 with other six wells targeting the Leduc formation, which are located far away, over 20 kilometers away from the main shock. And here we designed a large model, and we used exactly the same model architecture, the same as the smaller one, but the only difference is that we increased the distance to incorporate all these disposal wells. And here we show the simulation outcomes under different diffusivity setting. So the 4 panels on the right shows the map view of the pore pressure changes at around 1.9 kilometer depth within the Leduc formation. And under different diffusivity setting for the aquifers. So from 0.56 to 5.6 meters squared per second. So as the diffusivity value for the aquifer gets larger, the pore pressure diffusion gets faster. So as a result, the pore pressure will arrive much earlier when the diffusivity value is larger. So within the Leduc formation, the pore pressure contributions from the distant wells will surpass those of the nearby well 1418 when the aquifer diffusivity reaches around 4 to 5 meters squared per second, which corresponds to this lower right panel. However, according to our estimates for the diffusivity for the basal reef carbonates, we have some calculations here, which is not shown. If you are interested in that, we can talk about that in the Q&A session. But the maximum estimated diffusivity for the basal reef carbonates is around 0.4 meters squared per second, which is quite close to the first case shown on the upper left. So in this case, the pore pressure generated by those distant wells has not reached the main shock zone, which indicates these distant wells targeting the Leduc formation only have secondary role of triggering the seismicity in between November between 2022 and 23. Okay, so the third question is about what causes the seismicity resurgence. And there's one possibility in addition to the continuous injection is the triggering of the main shock. So here we calculate the stress changes triggered by the main shock and compare the stress values with the pore pressure changes values. So the tool we use is the static Coulomb beta stress changes. And there are two major elements in this modeling. The one is the source fault, and another one is the receiver fault. So the source fault is the fault that slips and transfers stress to the receiver fault. And the receiver fault is the fault that does not slip and receives stresses from the source fault. So here we first model the Coulomb stress changes induced by the foreshock main shock sequence. So we treat the foreshock main shock sequence as the source fault here. And the source fault, the center location and the dimension of the source fault is shown on this figure by this rectangle, grid rectangle, and the triangles indicate the dipping angle, the dipping direction of the source fault. And here we assume a specified receiver fault plane according to the source solutions from class B, so which is a reverse slip fault. And the focal mechanism is shown in the top upper left panel of this figure. So by assuming this specified receiver fault, we actually assume the receiver fault geometry across this 3D dimension is constant. So under this assumption, we are able to have a view of this 3D Coulomb stress distribution. And this image shows the Coulomb stress changes at the depth of 4 kilometer, And in this image, the red color indicates the positive Coulomb stress changes, and blue color indicates negative Coulomb stress changes. So the positive Coulomb stress changes indicate after the source fault locations, those locations will have higher possibility of subsequent seismicity, while this blue color indicates the main shock, the source fault will inhibit the subsequent seismicity. So this image shows a high correlation between the event locations and the Coulomb stress changes. So most of the events are located within the positive Coulomb stress change area. And this negative Coulomb stress change area, which is dominated by this source fault, form a seismically quiescent zone that inhibit further seismicity. So this actually indicates the foreshock main shock sequence trigger the majority of the following sequences observed in the following months. And we then further calculate the Coulomb stress changes induced by the two large events on March 16. And here we designed two individual source spots for these two large events, which are shown on its map. So we did a similar calculation, assuming a specified receiver fault. And the results shows that these two moderate events on March 16 mainly promote subsequent seismicity within class B in the southeast part. Instead, these stress changes decayed rapidly with distances, and it has very minor influence on cluster A. So now we extract these three large events and analyze their interactions among each other. So first, the main shock triggered 0.23 and 0.08 megapascal to these two large events, respectively. And between these two moderate events on March 16, there is additional 0.027 megapascal stress transfer. So this actually indicates this is a southeastward rupture cascade that is nucleated by this main shock. And compared to this pore pressure increase level, which is around 0.01 12 megapascal, this level of column stress changes is much larger than this pore pressure changes level, which indicates this after the main shock, the major triggers transition from the continuous injection to the earthquake interactions. So further, in addition, the reason why the rupture propagation was sort of terminated to the northwest is because the presence of the concrete structure, which acts as the low permeability barrier that probably likely restricts the northwestward fluid migration and rupture propagation. So to wrap up this whole story, we will use this interpreted figure. So to explain this hybrid mechanism behind the swaps. So we propose that these earthquake sequences likely reflect a cascading rupture cascade initiated by wastewater disposal, but mainly sustained by fault interplay. And the fluid injected into the well 1418 progressively migrate along the wave formation and penetrate the basement fault. And this basement fault was truncated by a concrete structure to the northwest. So as a result, this fluid was sort of confined to the southeast. And in contrast, the injection from these two shallow injectors were well isolated by the Ayrton shales and overlying actors on top of the Leduc formation. And this nucleation and evolution of the seismicity can be mainly divided into two stages. So the first stage is dominated by pore pressure increase. So the pore pressure within the after injection, after around 10-year injection, so the pore pressure slightly progressively increased within the basement fault, which reduced the effective normal stress and eventually triggered the main shock on November 30, 2022. And after that, the main shock triggered additional failure along the fault and leading to another two large events on March 16 and thousands of aftershocks. And due to the presence of this concrete structure to the northeast, the rupture propagation is mainly propagate towards the southeast. And the intersection between the main shock fault plane and the concrete structure form a linear fault zone, which is oriented for the strike-slip motions. So that's all for my talk. Thank you so much for listening. I would like to take the questions.
Awesome. Thank you so much. Great talk. I really enjoyed it. So I go
Oh,
through
thank
the
you.
question. Yeah. Thank you.
Uh,
Thank you for presenting. The first question is by Neil Watson. So first, he thanked you for presentation. The question is, it is generally accepted that seismicity in other regions, for example, KSMMA Montney, can be due to pressure transfer along through going faults to the basement. The Beloy Formation in the Reno area has well-documented faulting that causes lost circulation events from initial penetration until total depth in the basement, true depth in the basement. Why did your model not consider the possibility of pressure transfer along these faults?
that's a very good question. So because I have a few slides for the Q&A session, I'm going to show that. Actually, we did some simple calculations. Uh, let me see. So here, can you see the screen, right? You can see my screen, right? Still.
Yes. Mhm.
Okay.
You can put it
So,
on full screen to see
okay,
better.
okay.
Yeah, perfect.
So here, because in the simulation we talked in this presentation, we only assume these shield actors, the Ayrton shales and upper like Banff shales, Banff formation are act as perfect actors and isolate the pore pressure. from above layers. So here we further investigate if those actors are not are not doing a great job. So that's the reason we do this is we want to explore the contributions of this bellowy well. So here we just consider three different scenarios. So the first one is that we assume we just design some little fractures uh, across those actors and also those aquifers. So from the shallow to the basement fault. And you can see those pore pressures start to penetrate downward into this basement fault. And then a second scenario is we assume a weak actors, which means the diffusivity of those actors were very low, but still higher than the aquifers. So in that case, the pore pressure, there's small amount of pressure penetrating into the basement fault, which are generated by this below injection well. And third one is we assume this just totally absent of aquifers, and all the sediments are composed of aquifers. So in this case, the fluid pressure will just penetrate downward and go penetrate and go into this basement fault. So here we consider the pore pressure changes, and all these three scenarios only generate pore pressure level of around 0.001 megapascal within the basement fault, which is much, much lower than the pore pressure changes induced by the well 1418. So from so if we consider the pore pressure changes, I think this well it still has minimal or secondary contribution compared to the deep injection well. And then when it comes to the pore elastic stress transfer, we actually did a like simple calculation for this the analytical solution of the pore elastic stress changes under different diffusivity settings. And our results suggest, because I don't have a figure here, but I will just say this early. The results suggest only this pore elastic stress transfer will play a role in this seismicity triggering when the diffusivity is lower than 0.01 meter square per second. So we think this diffusivity is quite low, is too low if you consider all those aquifers because they much normally have higher diffusivity values. So to summarize my answers, so we think the proelastic stress transfers contributed by this parallel is still lower than the pore pressure increase generated by the deep injection well in the Leduc formation.
Perfect. Thank you. Next question is by Mauricio Canales. He said, thanks for the presentation. Question, how certain are you of the diffusivity
Thank you.
factor in the Leduc formation? He asked about
Certain.
how certain are you about the diffusivity factor in the Leduc formation?
Oh, yeah, this is a very good question. So another slide. So because I haven't done tons of simulations here and we have a sensitivity plot, I'm gonna share the screen. So this diffusivity value are actually obtained from according to previous studies and our sensitivity test here. So on the upper top part of the slides, we shows the typical regional permeability of the basal reef carbonates, which ranges around 10 to the minus 16 to 2 times 10 to the minus 30 meters squared. And this according to these literatures. And then we use this equation by assuming specific values. So here we take the upper bound of the range, the permeability range, which is 2 times 10 to the minus 13 meters, and use the specific fluid density, gravitational acceleration g, and we assume a dynamic viscosity value here, considering the temperature variation from 20 degrees Celsius to 80 degrees Celsius, and a specific storage value, which is 10 to the minus 5 per meter. And then we have the so-called max because we use the upper bound of the permeability. So here when we consider the temperature variations, we will have the range for the maximum diffusivity for the basal reef, the Leduc formation, which is around 0.17 and 0.54 meters square per second. So because in this modeling, we use a larger diffusivity range in our simulation, on the left panel, which shows this sensitivity test because we vary the aquifer diffusivity and we also vary the fault zone diffusivity, and they are shown along the x and y-axis respectively here. So because we have a further constraint according to this measurement, these calculations, we put two vertical lines here. So to indicate this estimated range of the aquifer diffusivity or the Leduc reef diffusivity. For the fault zone, actually, we don't have enough information to further constrain the diffusivity, but because all those studies, these studies and previous studies suggest the fluid migrate downward into the fault zone. So it's reasonable to suggest this fault zone is conductive, which means it has relatively high hydraulic diffusivity value. So this map shows the pore pressure changes, the average pore pressure changes as function of diffusivity, aquifer diffusivity, and fault zone diffusivity. And this value will peak when the fault zone diffusivity is around 1 meter square per second, and assuming it's a conductive fault zone. So we take this point, if you can see my cursor, as the optimal estimates. So we assume this is a conductive fault zone, so it's a 1 meter square per second diffusivity, and then we take the upper bound of this estimated diffusivity range for the Leduc reef. So that's how I obtain the so-called optimal estimates for the aquifer diffusivity.
So, as a follow-up question, do you change diffusivity from the minimum to the maximum versus depth? Is it changing from temperature 20 on the ground surface to 80 degrees C at the maximum depth to these values? Does it change with depth? Like
sorry,
basically, yeah.
are we talking about the second question by Mauricio?
No,
Sorry.
I didn't read the second question. I'm
Oh,
just
okay.
asking a follow-up question about change of
So,
diffusivity from ground surface to the maximum depth because of temperature gradient. As temperature is increasing with depth, we expect to have lower viscosity of the pore fluid, and because of that, diffusivity can increase substantially. Did you consider a linear trend of diffusivity with depth?
uh, actually, we did consider the diffusivity as a function of depth for the basement fault zone. Is that, let me find that slide. Uh, so the diffusivity here within the basement fault, within the background basement, except for the fault zone. So the diffusivity is a function of depth and it gradually decrease with the depth.
So
And
you
within the
consider
sediments, we
decrease.
actually, sorry, decrease the viscosity or diffusivity.
Yeah,
Are we talking about?
viscosity is decreasing, and because viscosity is
Yeah,
in the
viscosity is
decreasing,
decreased.
right? Because it is in the denominator of diffusivity
Oh,
equation, we expect that diffusivity increases with
yes.
temperature. Do you agree? Or
Yes, I agree. The temperature increase will lead to the decrease of viscosity.
Mhm.
Uh, but
And
here I
because of
think,
that, then it should be reverse of what you show here.
I see what your question means. Let me see. Because here in this model, we did use a diffusivity function as a function of varying depth, and the diffusivity actually decays with the depth, with the increasing depth. Uh, I think I will double check with the diffusivity setting here.
Mhm.
But actually, this diffusivity distribution is referenced from a previous study, so I will check with this. Thank you for this question. I
Sure.
think another issue is another factor that influence the diffusivity is, yeah, the when the temperature change, the diffusivity, the dynamic viscosity will decrease, but also the probably the specific storage will also change with a function
Mhm.
as function of depth.
Sure. Yeah.
And yeah, so thank you for the question.
Mhm. The second question by actually by Mauricio is it is feasible that the second magnitude 5 was caused by a stress transfer. However, keep in mind that the sequence has remained active since then, almost 2 years after the magnitude 5.6. So I would not disregard the statistical possibility. This is
Yeah,
just a
thank you.
comment. Yeah.
Yeah.
Next question is by Jens Lund Sni. He thanked for the presentation. If I understand correctly, the main shock was triggered by 0.01 megapascal pore pressure increase, which is extremely small. You mentioned that this is a previously suggested trigger threshold. First question, is that triggering threshold based on tidal stressing magnitudes? In other words, the fault the fault was essentially perfectly oriented for failure. Is that the case? Is the fault essentially perfectly oriented for failure? Okay.
Okay.
Get the answer as yeah.
Yeah, yeah. Oh,
So the second question
so
is
they okay.
the near perfect given the near perfect orientation, how do you entangle or distinguish between the influence of multiple possible triggering stresses which only need to exceed 1.5 psi, such as direct pore pressure triggering versus pore elastic triggering from either below or above? How do you distinguish between these two?
Yeah, so let me read the question again.
Mhm. He's asking about
Yeah,
direct
thank you,
pore
Wenhan. And
pressure.
to clarify, my question maybe is 1.5 psi is it seems like it would be within the error range for a lot of the estimates. So I'm kind of wondering how you even deal with something so small when you have multiple triggering factors. Maybe that helps.
Mhm.
Oh, thank you for the clarification. Uh, that triggering threshold phase. So for the first question, the triggering, the typical threshold is actually by that slide. Oh. So this threshold is documented in like is cited from the early studies, which actually I don't think is based on the tidal stressing magnitudes. Uh, in other words, the wind shock was
Okay, I'm thinking of work that I'm involved in by Peter Hennings and others for the Fort Worth Basin, where we're seeing I think the lowest pore pressure increases are on the order of maybe very small also, but maybe 15 or something like that PSI. But most of them are significantly higher than that, even for pretty well-oriented fault. So I was just kind of curious where this such low threshold came
Um, thank you for the question. So I still need to like digest this question further. Yeah, so I think I kind of got this question. So here, actually, the absolute value of the pore pressure changes or the stress increase are actually suffer from sort of uncertainties. So here, I think what really more matters here because is we are comparing the relative stress or pressure changes produced by the injection and earthquake triggering. So in this study, the relative stress increase, the stress changes actually matter compare rather than this absolute value. Because if we change the diffusivity value in our modeling, we actually have, like, let me see another slide. Sorry. So this is we did simulation under different parameter settings, ranging from a wide range of diffusivity. So this slide shows all the possible pore pressure increase within the basement fault. And actually they vary significantly from like even around below 0.01 megapascal to 0.012 megapascal. So the value varies significantly, but I think there are studies document the cases when the seismicity can still be triggered even below that level. So to summarize my answer, this threshold is like we just use it as a reference here, but we didn't uh, say this threshold is the true threshold for triggering the earthquake in our cases. So we're mainly comparing the relative contributions from different triggers.
Mhm.
Thank you. Thank you for the question.
Okay,
This is a very
thanks.
good question.
Okay, so great. The next question is by Pat McLellan. In comparison to many other fault reactivation studies in basement rocks, it strikes me that these are very small pore pressure changes in the order of 10 kilopascal that are claimed to be responsible. Did you also uh, conduct any deterministic fault reactivation calculations for the inclined faults and the estimated 3D stress state, orientations, etc.? May help constrain the pore pressure changes at play here. So did you consider other parameters of a fault?
Uh,
A stress state, orientation of fault, orientation of stress.
Yeah, that's a very good question. So in our simulation, we basically just assume the geometry of the fault, which is a northeast deeping fault structure, and with a deep angle of 40 degree. We actually did not consider this fault reactivation calculations for the specific incline fault and estimate the 3D stress state and orientations, etc. For this study, actually. So in our case, it's like more simpler simulation of pore pressure.
So as a future
Thank
study,
you.
maybe you should
Yeah, this is a
consider that.
very nice direction for future study. Thank you.
Perfect. Thank you so much. So we are on top of the hour. Thank you so much, Wenhan, for presenting for us. Thank you, everyone, for attending this webinar. I really appreciate it. As I mentioned, the next webinar is on December, and I look forward to seeing everyone in the next months for the new webinar. And thank you,
Thank
everyone,
you.
and have a great weekend. Thank you, Wenhan.
Thank
So
you so
we
much,
have,
Maddie, for
sure. Thank you.
yeah,
Thank you for
thank you.
presenting. So we have, if you have time, we can go to the informal section of this webinar, and if anyone wants to discuss their questions in person, they can unmute themselves and ask. And it is in case Wenhan still has time to just stay with us. Do you have
Okay.
time? Okay,
Now,
perfect.
right? Now.
Yeah, just now we
Yeah,
can
sure, sure.
proceed just for a few minutes if someone wants to
Sure,
ask
sure.
any
No
questions.
problem. No problem.
So I have a
Thank you.
question about your about cluster B. You showed the event clusters around the fault plane. So can you explain a little bit about the network that monitored that, like the side view? In the side view in the earlier slides. Okay, yeah, one of your slides. Okay, slide 23 maybe.
Oh,
Yeah.
this one?
Yeah, so the events are very close to that plane. Can you explain about the network, surface network that was installed to monitor those events? And
Yeah.
yeah, about the depth precision and stuff. Can you explain a little bit about the surface network?
the seismic stations, right? Like,
Yeah. Hmm.
I think I would use these. Let me find the slides. We talk about the stations, we call it
Yeah.
seismic instrument or something.
Yeah.
So this rectangle indicates the location of the main shock, but
Mhm.
before we deploy the and our local nodal array, there are actually only four Raven stations, which are installed by the AGS, the government. So they are only four stations available within 70 kilometers away from this main shock. So this is quite a sparse station distribution, which leads to some their even locations for those previous studies actually have relative high uncertainties here. And then after the main shock, 1 week after the main shock, we collaborated with our collaborators and install 10 nodal geophones, which
Mhm.
is in the closest proximity to this cluster, this
What is
main
the
shock.
area? What is the area size, for example? You
Oh,
mentioned that, yeah.
it's only around less than 10 by 10. It's maybe
Mhm.
5 by 10. Maybe the length, the horizontal dimension is maybe only 7 kilometers.
Mhm.
And the horizontal one is slightly longer, maybe 10 kilometers. So this is quite local
Mhm.
array.
Perfect. Yeah.
And
That looks
then that's
amazing.
why we are able to, yeah, identify thousands of aftershocks, which
Mhm.
is really great.
Yeah. I have another question about the sequence, temporal sequence of the events that you showed in Leduc. It goes toward the southwest and then it goes toward southeast. So I was
Um,
wondering,
this one,
yeah.
temporal
So
sequence.
yeah. So do you have any temporal sequence of these events? Which one happened
Yeah, yeah.
earlier? Which one happened later?
Oh,
And
oh,
you see how they are migrating toward the main fault in cluster B.
I see.
So it can be
So,
understood it if another fault is basically a minor fault towards southwest is contributing into the transfer of this pore pressure toward the main fault or not, and then based on that you can tune the diffusivity of the Leduc better than this case that you assumed no fault towards southwest, right? So basically, from the point that you are just showing for cluster B, yeah, over there, we see the. I assume that there is a trend of these events towards southwest first, and then it moves towards southeast. Do you agree? Or
actually, I think you were talking about the temporal distribution,
Mhm.
temporal evolution of these
Yeah,
two sequences. We actually
yeah.
have a figure I can show you that. Uh, Let me see. Oh, oh, I think, it's here. So let me hear. This one is better to answer a question here.
Mhm.
So we also just we bin all those events into 2D interval, and these histograms count the number of events within each time bin.
Mhm.
And this red and blue color indicates the histogram for cluster B and A. So here, what we observe from these two clusters is that they form two temporal sequences. So the first one is actually was initiated by the ML 5.6 event, and the second one is was initiated by the two large events on March 16. And
Mhm.
we fit modified Amori's law to these two sequences, so which shows a quite good fitting to this modified Amori's law. So this Amori's law indicates this is a power law distribution which indicates uh, main shock, foreshock, main shock, aftershock sequence is similar to the natural earthquake. So it's like the main shock triggered 1,000 aftershocks. Those tails
Mhm.
are actually triggered by the main shock.
Mhm.
And
Wow.
this
Okay.
4 months later, these two large events triggered another sequence. So in our case, because we did not find some very obvious temporal migration of the swarm starting from the injector towards somewhere like to the southwest or to the southeast or northwest. But in our case, so after the foreshock mid-shock sequence, we immediately observed those two clusters along, which are observed here.
Mhm.
And we did not observe any clear migration of the swarms, which are indicative of the fluid migration, right?
Yeah, I was looking for that.
Actually,
Like,
we did not observe a clear pathway of
oh,
those. So
oh,
it's so that's why we think it's a hybrid mechanism behind these sequences, like related to the tectonic fault interplay. Yeah,
mhm.
it really plays a role here.
Yeah, it would be great because in your numerical model for fluid flow, you could see the progress of the pore pressure plume migration from one area to the other. But if you could assign times to these events and they progress in some specific direction, you could compare those numerical model results in time versus this sequence of events in time. Yeah.
Yeah, yes. So that's great. This,
Yeah, perfect.
thank you.
Sure. Thank you so much. It was very interesting talk. I really enjoyed it.
Thank you. I was really nervous preparing for
No
this
problem.
talk.
No problem. No, I think you went very well. Thank you.
Thank you.
Is there any other question by the audience? They can just unmute themselves and ask.
Oh, I missed how was the pressure? I think there's
Yeah.
another one, right? How was the pressure on the basement fault determined? Oh, yeah. So this basement fault pressure was determined from our simulation because the model we designed here, I can show the diffusivity. This is a section depth view of the diffusivity section. The fault is a conductive fault and high diffusivity, and is connected to the Leduc reef formation. And then as a result, the injection into this Leduc reef formation migrated along the basal sediment, sorry, not basement, basal sediment, and then go down into the basement fault structure. So the estimated pore pressure uh, is from the simulation and because of the architecture we designed for this model, right?
So
Hi,
just
it's Michelle
yeah,
here.
hi, Michelle.
Yeah,
Just please
I was
go
just
ahead.
curious if you use the injection pressure from that disposal well to determine the
Oh,
rate
actually,
along the fault and stuff.
yeah, yeah. Oh, so I think the injection pressure for most of the disposal wells are not available
Right.
for us. So I didn't find the public data for the injection, but there are some injection pressure for some of the wells, but not near our target region here. So
Okay.
thank you.
Okay.
That's a very good point.
Thank you.
If we have the injection pressure, that would be really helpful for this study.
Awesome. By the way, we have a study, hydromechanical study of Venus earthquake sequence that happened in 2015 with magnitude 4. So we obtained something similar trend of the pore pressure migration within Ellenberger that activated a basement fault. I'm just going to post the link to that paper for your reference. It's a pretty interesting similarity between this work and the work that we did for Dallas Fort Worth Basin for Ellenberger and Venus earthquake.
Thank you.
So
Thank you.
yeah,
That's been
so
great.
yeah. Any other questions?
Thanks, Wenhan. Thanks, Madi.
Thank
Sure.
you. Thank
Thank
you
you
for
so
a
much.
question.
So if there is no more questions, we can close the webinar here.
Oh, okay.
Yeah. Thank you so much
So
again, Wenhan. I
thank
really
you.
appreciate it. If you have final thoughts, we can hear. Otherwise, we can close the meeting and see everyone
Okay,
in the next
I'm good
month.
now. Thank you so much for your invite and the
Sure.
hosting the meeting. It's very interesting meeting. A very
Sure.
nice
Thank you
meeting.
so much. Yeah, I'm going
Thank
to
you.
share the paper with you via email.
Oh, that'd be great.
Sure. Thank you.
Thank you.
Have a great
So
weekend,
have a
everyone.
great
Thank you.
weekend. Thank you.
Thank you.